Welcome to this explainer. Today, we're doing something pretty huge. We are demystifying the literal building blocks of our entire universe. I'm so excited to take you on this journey through the very substance of reality, to look at exactly what makes up, well, everything.
Let's just dive right in with a quick question to get the gears turning. What actually connects you, a star burning millions of light years away, and a simple ice cube sitting in your freezer? I know, it sounds like a trick question, right? But the answer is the fundamental key to our physical reality. You, the star, the ice cube, you're all made of matter.
Here's our quick roadmap for today's explainer. First, what exactly is matter? Then, we'll hit the 4 fundamental states, look at physical versus chemical properties, dive into physical and chemical changes, and wrap up with compounds versus mixtures.
All right, Section 1. What exactly is matter? Let's define existence.
So the crucial takeaway here is that matter is basically anything that has mass and takes up physical space, meaning it has volume. It's the stuff making up all the physical structures we see and touch every single day. The atoms in the screen you're staring at, the air you're breathing right now, the chair you're sitting on, it's all matter. And the actual amount of matter in a given object, that's what we measure as its mass.
And water is the absolute ultimate model for understanding this. It's uniquely perfect as a case study. You've got 2 hydrogen atoms and 1 oxygen atom. Good old H2O. But what makes it so special for us is that it naturally exists as a solid, a liquid, and a gas right here within Earth's normal temperature range. Because we interact with it in all 3 forms constantly, it's just the perfect baseline for understanding how matter behaves.
Moving on to Section 2, the 4 fundamental states, or the forms matter can actually take. Now, it's fascinating to see how these particles practically take on distinct personalities depending on their state. In a solid, like ice, they're locked tightly in place. Definite volume, definite shape, vibrating just a little bit because the forces holding them are so strong. Now, in a liquid, the volume stays definite, but the shape becomes completely variable, adapting to whatever container you pour it into since the particles are free to slide around each other. And then in a gas, like water vapor, both volume and shape are variable. Those particles are just zipping around at incredibly high speeds.
But hold on, beyond gas, we've got a 4th fundamental state, plasma. When you expose a gas to extreme, intense heat, the electrons are literally ripped right away from their atoms. This forms a highly conductive sort of sea of freely moving electrons and positively charged nuclei. Because of this electron sea, plasmas are incredibly electrically conductive and respond super strongly to electromagnetic forces. Think lightning strikes, electric sparks, or even the glowing neon signs down the street.
Now, you might be thinking plasma is some rare anomaly, but actually, scratch that. It makes up more than 99% of the visible material in the entire universe. 99%. Basically, all the visible light we see from deep space comes from stars, and stars are just massive balls of incredibly hot, high-energy plasma. So sure, solids, liquids, and gases completely dominate our daily earthly lives, but plasma? Plasma completely rules the cosmos.
All right, Section 3. Physical and chemical properties. How we actually identify these substances.
There's a pretty stark contrast in how we go about identifying matter. Physical properties are totally independent of a substance's actual chemical makeup. You can measure them without changing what the object fundamentally is. But chemical properties? Those only reveal themselves during a transformation, when the matter is actively becoming an entirely new substance.
To give you an idea, here are some physical properties we can measure right off the bat. Things like color, texture, or hardness, stuff we can observe with our senses or just basic tools. And remember, properties like density, color, and melting points are what scientists call intensive properties. That's a fancy way of saying they do not change no matter how much of the substance you're holding. A tiny gold ring has the exact same density and melting point as a massive gold brick.
On the flip side, we have chemical properties, which describe a substance's tendency to react. Flammability tells us how something burns in oxygen. Toxicity tells us how it might harm biological life. And reactivity, well, that can be incredibly dramatic. Take potassium, for example, a highly reactive element. If you take a tiny pea-sized chunk of potassium and drop it into just a little bit of water, it reacts explosively. Bam! But the catch is, you can only observe that explosive property by letting the potassium fundamentally change chemically.
On to Section 4, physical and chemical changes. Let's look at how matter actually transforms.
So, think about coloring on paper with a crayon or, I don't know, picking tomatoes out of a salad. You're making a physical change. The crayon wax is still wax, the paper is still paper.
It's purely physical and usually pretty easy to reverse. But when a metal bike rusts out in the rain, that is a chemical change. The iron in the bike is chemically bonding with oxygen in the air to form an entirely new substance, rust. And because a brand new substance is produced, chemical changes are definitely not easily reversed. I mean, you can't just physically scrape the oxygen out of the rust to get your shiny iron bike back.
Let's break this down into a step-by-step process of phase transitions. By continuously adding heat, we literally force matter through distinct physical changes. A solid melts into a liquid at its melting point. Add more heat, and it boils into a gas. Add extreme heat, it enters that plasma state we talked about, where electrons get ripped from their parent atoms. These abrupt structural shifts are phase transitions, entirely dictated by temperature and pressure.
But as always in science, the rules can get pretty weird. We actually have these bizarre transitional states called supercritical fluids. If you push a gas way above its critical temperature and pressure, the distinct boundary between liquid and gas completely vanishes. You get this crazy fluid that expands to fill a container like a gas, but has the heavy density of a liquid, making it an incredible solvent. Seriously, supercritical carbon dioxide is exactly what manufacturers use to safely extract caffeine and make your decaf coffee. How cool is that?
Finally, Section 5, Compounds versus Mixtures. This is all about combining matter. Just like with physical and chemical changes, the specific way things combine completely dictates their final form. When substances combine physically, they make a mixture. Stir some salts into water, you get salty water. The mixture keeps the properties of the individual substances and you can still separate them out. But when elements join together chemically, they form a compound. And here's the kicker. The properties of a compound are often entirely different, completely unrecognizable from the original elements that created it.
Let's look at the sheer magic of compounds using glucose, the sugar sitting right there in your morning cereal. It's made of carbon, hydrogen, and oxygen. Now, out in nature, carbon is a brittle black solid, like coal, or a super hard clear solid, like a diamond. Hydrogen and oxygen? Both invisible, completely odorless gases. But when you chemically bond them together, boom, you get sweet white sugar crystals. You literally take black coal and two invisible gases, and you get sugar. That is the unbelievable power of chemical compounds.
Before we wrap up this explainer, I really want to leave you pondering non-classical states of matter. We've talked about the big four, but consider the glass in your windows. Glass is technically a non-crystalline or amorphous solid. Thermodynamically speaking, it's frozen in a metastable state. It completely lacks the regularly ordered repeating crystal patterns of a true classical solid, which means it sits in this incredibly fascinating in-between territory of physics.
So as you look around at the physical world today, from the water in your cup, to the plasma burning in the stars, to the liquid crystals literally flowing inside your TV and phone screens right now, ask yourself, what other hidden, bizarre mysteries of matter are just waiting to be explored right in front of your eyes? Keep observing, keep questioning, and I will see you in the next explainer.